This would be question number 61A from section 15.2. It has, so this part has statement like this. It gives you a statement and it asks if it's true or false, and then it asks for explanation or counterexample. The statement is like this. If the limits of this function f of x, f of x and y, along a path where y equals 0, you see this y equals 0, and x approaching 0, and this same limit, but now with x equal to 0 and y approaching 0, exist and equal to L. So these two limits equal to L. Then the limit of this function as x, y approach 0, 0 equal to L. Let me draw this. What this statement is saying is that if the limit of a function while we keep y equals 0, let me use some color. While y equals 0 equals to L, so this guy approaches L, and while x is equal to 0 and y approaches 0, the limit is also equal to L, then the overall limit is equal to L. Now, let's think about it. Remember how in lecture you talked about every, for the limit to be L, it would mean that every single path you can think of would give you the same limit. Now, the statement only gave you two paths, right? Not every single path that's imaginable. So then the speculation is that this is false. Actually, not speculation. It's just a false statement. The reason why is because y equals 0 and x equals 0 are only two paths. And you can probably think of some other path where you'll have a different limit, or maybe no limit at all. And here I highlighted the two paths that correspond to this picture and this. Let's think of counterexample. I claim that this one is counterexample like this. Let me show you why. So for this example, when you're approaching along the path where y equals to 0 identically, you would need to plug in y equals 0 everywhere here, and then x stays as is. So then this is just a limit as x approaches 0 of what? Well, on the top, we have some number close to 0 times identically 0. On the bottom, we have identically 0 plus a small number. So let's rewrite this. This is basically identically 0 over x squared. And this limit is going to be 0. So this is this L that's in the question. Okay, so this is limit along this path. Let's find the limit along the red path. We have x equals to 0 identically, and then y is just some small number close to 0. So then again, we get limit as y approaches 0 of 0 over y to the 5th, and this is equal to 0 again, so same number L. Now what happens, for example, if you approach along the path x equals to y? In this case, you get a limit as x approaches 0 of what? X stays as is, and then instead of, actually I should be using a different color. X stays as is, and instead of y, we plug in x. So then we get limit as x approaches 0 of x squared over x squared plus x to the 5. Let's cancel x squared on top and bottom. And the reason we're allowed to do that is because when we're talking about limits, we don't care about x being identically 0. So we're allowed to actually cancel it. So we get something like this. And then this guy is approaching 0. So then we get 1 over 1, which is 1. So you see, this is a different limit. So then this counterexample shows that by considering some other path, we can easily find an example where a limit is different. Okay, let's do next part. This would be part B, and the question, the statement says that if the limit of a function as x, y approach a point AB equals to L, where L is some finite number, then the function f is continuous at AB. Now this statement is false as well. Let me explain why. Let's recall from the lecture the definition of continuity of a function at a point AB. You need 3 conditions. Function f needs to be defined at a point AB, the limit needs to exist, and the limit needs to be equal to the value of the function. Now the only condition that's satisfied when you have this is this one. So this one is satisfied, that's no problem. But then nobody told you that f is necessarily defined at a point AB. So this is not given. And this is not given because, okay, sure, maybe f is defined, but what if it's different from the limit? What if it's different from L? Let's get a counterexample. First counterexample is where the function is just not defined at a point AB, and it could be something as simple as this. Function would be L plus X plus Y, where, oh, sorry, okay, AB, in this case, what I had in mind is AB equals to 0, 0. Because we want the limit to be L, right? So then, because you see, limit of this guy is L when X and Y approach 0, 0, because you can just plug in X and Y. Now, the function is not defined at this point of question, so then the function is not continuous at AB equals 0, 0. Same idea here, again, 0, 0. But now f is defined at a point 0, 0, but the limit is different. So here you have the value would be L plus 1. So f at AB equals L plus 1, while the limit as x, y approach AB of the function is equal to L. So these are different. So this guy is also not continuous. At the point AB equals 0, 0. In part C, the statement is like this. It says if f is continuous at a point AB, then this limit at the point AB exists. This statement is true because of the definition of continuity. Continuous means these three statements again, and one of these statements, the second one, is exactly the statement that we're after. So exactly this. Let's do the next part. The next part says it says if Q is a boundary point of the domain of a function f, then this point Q is in the domain of f. So it says if it's a boundary point, then it's in the domain. This statement is false because it's not necessarily true. You can have a point that's outside the domain and still is a boundary point. Let's recall from the lecture what boundary points are. This point Q shown here is a boundary point. It means that every disk that's centered at Q contains a point in the domain and outside the domain. There is no requirement that this point is in the domain. It just means that in this disk there would be points inside and outside the domain. So then counterexample would be like this. F of xy equals to ln of x. Let me sketch the domain. Let's make it in red so it's more visible. You see, if x is greater than 0, everything is fine. If x is less than 0, then we're outside the domain. And if x is equal to 0, we're also not in the domain. That's why I'm drawing a dashed line to show that it's not included in the domain. And let's consider any point Q where x equals 0. For this point Q, no matter what disk we take, it will contain points in the domain and points not in the domain. Sorry, not in domain. And this is in the domain. So and no matter how small we make this disk, this will always be the case. So Q is a boundary point of the domain. But it's not in the domain. X equals 0 is outside of the domain. So Q not in the domain. Let's do the next question. This would be number 27 from 15.2. You're asked to find a limit like this of this fraction here involving square roots, and we have x and y approach 1, 2. First thing, let's at least understand how this 1, 2 has to do with the domain of this function here. We have, so what's the domain? We want our y to be 0 or above. This is what I wrote here. We want x plus 1 to be 0 or above, which is the same thing as saying x is greater or equal to -1. That's what I wrote here. And we also want the denominator to be non-zero. For this, we want y to be unequal to x plus 1. So then the domain is everything except, well, no, not everything. Okay, so it's y greater or equal to 0 and x greater or equal to -1. And then y is unequal to this. So this line is excluded from the domain, and everything else is included. What is this point 1, 2, where we want the limit? This is here, oops, and here. So it's actually on this line. So it is a boundary point of the domain, which is outside of the domain. So it's a problematic point. This is the point where the denominator is 0. So we can't just plug in numbers and hope to evaluate the limit that way. What we do instead is we use the method from lecture where we multiply by the algebraic conjugate of this expression with square roots. This is what I did here. This part is the algebraic conjugate. Next thing we do is we multiply out this part. You see, this is a formula for difference of squares. It's kind of like a minus b. Let me use black. It's kind of like a minus b times a plus b. We know that it's equal to a squared minus b squared. So then this guy becomes square root of y squared minus square root of x plus 1 squared. This is equal to y minus x plus 1, and that's it. So then this becomes y minus x minus 1 once we expand this out. The denominator is just the product of these two things. Then this is equal to, this part cancels, and we're left with 1 over this guy. Now we can, well, I'd say on a test you can just plug in the values at this point, because as long as these guys are not negative, you can just plug in these values. I'll show you using this theorem 15.2 how to show it. So you see that we have a quotient 1 over something. We also have square roots and we have a sum. When we have a sum, we can just add up the limits. When we have a square root, this is actually this case. As long as these guys are non-negative, the stuff inside the square roots, then we can just plug in these numbers to find individual limits. And you see that at this point, we're well away from the locations where these things under the square roots can go negative. So then square roots are not a problem. And then we also have a quotient. Quotient would only be a problem if denominator is 0. And in this case, you'll see, I'll start evaluating it and you'll see that it's not a problem. So let me just plug in the values. You get 1 over square root of 2 for y plus square root of x plus 1. So 1 plus 1. So you see denominator is not 0. So we get 1 over. This is also square root of 2. So we get 2 square root of 2. And that's the answer. Let's do problem 31 from section 15.2. You are given a limit like this of this rational function y to the 4th minus 2x squared over y to the 4th plus x squared. And you want to find the limit as x, y approach 0, 0, or you want to show that the limit doesn't exist. Let's speculate that the limit doesn't exist, and to show it, we'll use a two-path test and see where this will take us. The paths I tried at first were y equals to mx. These are the paths I'm showing here. So they would be straight lines converging on the point 0, 0, which is where we want to find the limit, remember? So then this limit becomes this expression, which is the same thing as here, but now instead of y, we have m times x. Then here I'm expanding this, I'm getting m to the fourth x to the fourth, and same thing here, m to the fourth x to the fourth. This is equal to, let's cancel x squared on numerator and denominator. This way I'll get x to the 2 here. This x squared cancels. This becomes 2. And this cancels, and the whole thing becomes 1. So then we get m to the fourth x squared minus 2 over m to the fourth x squared plus 1. This is equal to, x approaches 0, so then this term approaches 0. Same thing for this guy. And we get negative 2 over 1, which is negative 2. Okay, so this kind of paths gives us limit of negative 2. Now, a lot of students, when they see this, they conclude incorrectly that the limit is equal to negative 2. Now, the reason this is not the right conclusion is because we've only considered one kind of path of this form. This is not all possible paths. It's just one possible kind of paths. So then let's try to use another path and see if the limit is the same. Now, if this gives us the same limit, we still haven't really shown anything. So then you really shouldn't be using this two-path test to show that, to find the limit. Two-path tests are for showing the limit doesn't exist. Okay, so let's see. Well, this didn't work. Let's try x equals my. Now we have limit as y approaches 0. Now instead of x, we're going to plug in my. So that's what I got here. I expanded my squared, so I got m squared y squared. Same thing here, m squared y squared. This is equal to, let's cancel y squared again. So we get 2 here, 2 here, and these cancel. So we get this y squared minus 2m squared over y squared plus m squared. Now, this has two cases. One case is when m is a non-zero number. In this case, we can just see that y approaches 0. When this happens, we get negative 2m squared over m squared, and then these guys cancel, and we get negative 2. Now, when m equals to 0 exactly, that's where we have this situation. We get the limit of y squared over y squared, because this guy is just 0. And this limit is equal to 1, because this cancels. So you see that these two limits are different. So for these kind of paths, let me show them maybe in red. They're also straight lines, but we got a different kind of limit when m was equal to 0. So this is the case where x is identically 0. So maybe let's use purple for that. So when x is identically 0, we got a different kind of limit. So then by two-path test, the limit doesn't exist. Now, In the textbook, actually, they tell you that the limit doesn't exist and ask you to use two-pass test to show it, but I just wanted to make it slightly more difficult. Next is question 77 in 15.2. In this question, you're given this function that's defined in this piecewise manner. It has this kind of expression when x squared plus y squared is not equal to 1, which, by the way, is when the denominator is non-zero. And then when this denominator is 0, we have a value of b. So this is it. Now, you see that if I transfer 1 to the left-hand side, I'll get the denominator. That's why I'm saying when the denominator is 0, that's where you get this expression. And this is the value of the function in this case. Let me sketch out this situation. What we have is this. We have that the function has a value of b on a unit circle. This is the unit circle equation. And everywhere else, it has a value like this one. And the question then asks, find the value of b for which f is continuous at all points on the xy plane. Now, first, let's understand that this guy will not give us any problem as long as we're not on the unit circle. So at any point outside or strictly inside the unit circle, this function is continuous. So irrespective of what b is. The reason why is because this polynomial will not give you any trouble. Sine of a polynomial is also continuous. And then when you divide, the only thing that can go wrong here is denominator being 0, but that only happens on the unit circle. So everywhere here and here is not a problematic point. The only problematic set of problematic points is the set of points right here. The ones where x naught squared plus y naught squared is equal to 1. To figure out the value of b, we can simplify this problem a little bit. We can write this function as a composite function. We know that it's equal to some f of u. Well, I'm going to write it as f1 because I don't like when function with 2 arguments suddenly becomes function with 1 argument, but I could have just used f. So this guy is equal to sine of u over u if u is not equal to 0. You see, I'm using the equivalence of this statement to the statement x squared plus y squared minus 1 not equal 0, where this guy is u. This is u, and this is the same quantity, right? So it's also u. And it's equal to b if u is equal to 0. And this u is equal to x squared plus y squared minus 1. And what we will use is the theorem for continuity of composite functions, which essentially tells you that if this guy is continuous at this point in question, and if this guy is also continuous when we have x naught, y naught plugged in here, and you get some value for u, if this guy is also continuous at that point, then the composite function, which is this guy, is also continuous. So let's see here. This u function is x squared plus y squared minus 1. This is just a polynomial, so it's continuous at an arbitrary point on the unit circle and is just continuous wherever we look at the xy plane. The only thing in question is f1 of u. This guy, if we want it to be continuous at this value of u, I'm actually going to put u naught here to be consistent with these guys. What we want is that the value of this function equals to the limit of this function as u approaches this value 0. Oh, I haven't explained how I got the 0. Well, I got 0 from, well, you could say from here, or you could say, okay, x naught squared plus y naught squared, we selected it in such a way that this guy is equal to 1, so this guy is 0. Okay, so we want the limit as u approaches 0 of this guy to be equal to b. This limit is the same one as the limit of this part. The reason why is because limits talk about behavior near some point, near 0, not at 0. So this is at 0, this is near 0. So we always want to select the value that's near, not at a point. So then once once we plug in this expression, we can evaluate this limit from first year calculus, and we know that this limit is 1, which means that b has to be equal to 1. Question 67 from 15.2. This question asks you to use method of your choice to get this limit. This one, I don't really know how to approach it using either factoring numerator or multiplying by conjugate or simplifying it in some sort of way. I can't really think of anything, so maybe the limit doesn't exist. So let's try showing that this is the case using a two-path test. So the first path I've tried was y equals 0. Well, the reason I didn't really try hard finding this limit, but two-path test is a really simple thing to do, so why not just try using it and seeing what happens? When I plug in y equals 0, I'm left with x being the only variable, so I have this x here, and then instead of y, I plug in 0. So then I get absolute value of x over absolute value of x here, and then this is the limit of 1, which is just 1. Now let's try, oh my god, what happened here? Okay, I'll fix that. Okay, I tried another path where x is equal to 0. Here I plugged in 0 for x, and then I'm left with negative y divided by y. So then again, you see absolute value of negative y is the same thing as absolute value of y. So we again get 1. So at this point, still, we haven't concluded anything at all just yet because we only considered two paths. We need to consider, more paths than that. We can't, just because these two are equal doesn't mean anything. Okay, let's try another one. Y equals x. By the way, the reason I'm trying y equals x is because I keep getting 1 here, so I want to do something else. I'm actually I looked at this and I thought, okay, how do I make it something else? Let's say 0. Well, a way to make it 0 is to make this guy cancel. So x equals y, which is exactly the path I'm trying here. And that's what I'm going to do. I'm going to plug in x for y. And the only variable here is x. So then here we get limit as x approaches 0 of x minus x, which is 0, and at the bottom we get 2x. So this is just limit of 0. So then we get 0, which is different. Now, one note of caution, I started plugging in those paths without explaining why I'm choosing them. Well, the point of interest is 0, 0, right? So this is the point right here. So this path is the path where y equals 0. You see, it does converge on this point. If my point of interest was over here, I wouldn't be able to use this path. This path doesn't converge on this point. Path x equals 0. Oh, and this path gave us 1. Path x equals 0 gave us 1 as well. And path y equals x which again converges on this point, gave us 0. So limit along different paths is different, so by the two-path test, the limit doesn't exist. Now, if you're curious, I've plotted this function using MATLAB, and that's what I got. So you see that along the red line, we had this cyan color, which corresponded to 1. Actually, the value of the function is just exactly 1 on this line. Let me just double check. Yeah, right, because we plugged this in and then it just canceled. So there was no actual evaluating the limit. We actually just determined that the value is equal to 1 on this line. I mean, not on this point, obviously. On this point, you're dividing by 0. Okay. Sorry, this was this red path right here. The blue path, same thing. We have this cyan color, which corresponds to 1. Everywhere on this line. And then on the line y equals x, we have this. Problem 77 in 15.3, you are given a function like this, is defined in a piecewise manner. The first part is for x and y not equal to 0, 0, it's equal to this fraction, and you can see actually exactly at x, y being 0, 0 is when this part is not defined. But at 0, 0, the value of the function is exactly 0. So here it's this, and everywhere else it's this. And the question asks, is the function continuous at the point 0, 0 right here? First, let's get the value of the function at 0, 0. This we're given is equal to 0. I'm using this version, this part. Next, let's find the limit at 0, 0. The limit is equal to, let's see, again, which version should we use? Should we use this one or should we use this one? Well, limit means the behavior around the point of interest, right? Not at the point of interest. So to determine behavior around, we need to look at this portion. So we're going to use this one and plug it in here. And then let's see. Well, I don't really see how to simplify this expression, so let's just speculate that the limit doesn't exist and try to prove it using two-path test. The paths I've tried were y equals to m times x. So here we will be left with only x variable, which will be approaching 0. So, oh, sorry, one thing I forgot to mention again, y equals mx are paths like this or like this that you see they converge on the point of interest, which is why those are good choices. Okay, so we are filling in these blanks. Here we have, I'm using this guy. We have x. Here we have y, but y is now equal to mx. Here again we have x, and here we have mx. This is equal to limit of negative. Again, fraction, we have mx squared over x squared plus m squared x squared equal to limit. Let's cancel x squared. We will get m divided by 1 plus m squared. So you see that the path depends on the value of m. So on the choice of the path, depending is it this one or is it this one, etc. Which means that the limit does not exist. If the limit does not exist, it's enough to show that the function is discontinuous. So the function is not continuous. Okay, so this is it for part A. Let's do part B. In part B, the same function, but now the question asks, is f differentiable at 0, 0? Now, I'm going to use this theorem that you guys covered in class. It says that if a function is differentiable at a point, then it's continuous at this point. So the answer to this question is no, the function is not differentiable, and I'm going to prove it using contradiction. So I'm going to assume that the function is differentiable at 0, 0. This means that by this theorem, that the function is continuous at 0, 0, right? But we just shown in part A that the function is not continuous, right? So this statement contradicts part A. This means that the function f is not differentiable because we just got a contradiction. So our assumption right here was incorrect. Differentiable, so this is incorrect. So this is not differentiable. Next part is part C. In part C, you are asked to evaluate the partial derivatives at a point 0, 0 if possible. So same point where we found the function to be discontinuous. We want to evaluate these derivatives. Remember in class you covered how to find partial derivatives at a specific point using the definition directly. So that's what we're going to use here. First, let's find partial derivative with respect to x. I'm going to use this formula. So a would be 0 and b would also be 0. So we're going to have 0 plus h, and here we're going to have 0 for b, and then we're going to have 0, 0. Then we need to decide which which part of this function we're going to use for which point. So the point h0, h0, this one, is located somewhere here. I'm going to show it in blue. The point h0 is here. It's really close to 0, 0 because h, when we are talking about limits, is extremely small, but it's not identically equal to 0. So we cannot use this value. We are going to use the value here. So this would be this one. Let me highlight it. This is going to be this value. So that's the one we're going to use for this point. For this point, we are going to use the value identically at 0 because this is exactly what this guy is giving you. So then that's why here we have this 0, which is the value of the function at 0, 0. And here we have this big expression, which we will fill in a moment. Let's see what we should be using there. You see, it's a value of x is h, value of y is 0. So we have value of x is h, y is 0, x is h, y is 0, x is h, y is 0. Then we have h times 0 divided by h squared. H times 0 divided by h squared, h cancels, and we get 0 over h, which is identically 0 because h is non-zero. So then we have 0 minus 0 divided by h, which is 0 when we evaluate the limit. For this one, I'm not going to show you the details, but you'll use this formula instead, and instead of x, it's y that's going to have h added to it, this h, and then you'll get really similar calculations to get to the same answer. In part D, you're asked to determine whether fx and fy are continuous at 0, 0. I'm only going to actually focus on fx, and fy logic is really similar. First thing we'll do is we'll try to figure out what this fx is, because we've only found out that fx at 0, 0 equals to 0, but we have no idea what happens around 0. So for points that are not at 0, 0, so for points away from this point, so somewhere, say here, our fx of xy is given by the partial derivative of this expression over here. The reason why is because when we're away from this point, our function is just given by this guy, so we don't need to worry about the value of the function at 0 at all. We don't need to worry about the denominator being 0. So there is nothing preventing us from just using the differentiation rules, like the quotient rule. So let me just label that. Okay, so then we use the quotient rule, which is what I'm doing here. This minus is here. Then I have derivative of xy, which is y. Well, it's derivative with respect to x, right? So we're keeping y constant. Then we have the denominator. Then we have minus xy, which is the numerator, times the derivative of the denominator. And then on the bottom, we have denominator squared. Then I've expanded this out. So I got x squared y plus y cubed. And then for this guy, I got 2x squared y, 2x squared y. Then in the next step, I collected these two like terms. So I got negative x squared y. and then plus y cubed, that just stays. Then I put this negative into the numerator, so I swap signs here, and that's what I got for this derivative. Now the expression for fx is like this. When x and y are not equal to 0, 0, we have this expression that we just found. When x and y are 0, 0, we have this. And that we found in part, I think that was part C. Yes, that was part C. So that is from part C. So now you see that now the problem of continuity of fx is the same as we had for just f. We have this piecewise defined function, and we're just trying to figure out if it's continuous. So we do the same thing as before. We evaluate fx as 0, 0. Remember, the value was 0, is this one. Then we find the limit at 0, 0. This is equal to, well, this limit is equal to the limit of this top function here. I'm going sort of quickly here because we've just done something really similar. Okay, so for this one, I'm going to speculate that the limit doesn't exist, and I will try using two-path test to show it. I will plug in x equals 0 for the path. Again, path x equals 0 is one of the paths that are converging on the point of interest. That's why I'm choosing this path. Now we'll have the limit as y approaches 0 of, let's plug in x equals 0, so we'll have 0 squared y minus y cubed over 0 squared plus y squared, all of this squared. This gives us 0 for this guy, and then we have negative y cubed over y to the fourth. This is equal to limit as y approaches 0 of 1 over y. And actually, this limit doesn't exist at all along this path. That's one way of thinking of it. Another way of thinking of it is that the limit as we approach from this side is going to be plus infinity, and the limit as we approach from the negative side is going to be negative infinity, because that's what happens when y becomes extremely small negative number. So in either case, what we get is that this limit doesn't exist. So then this fx function is not continuous. At 0, 0. And the same thing for fy. If you go through the same steps, you're going to get the same answer. In the next part, you're asked to explain why theorems 15.5 and 15.6 are consistent with the results in parts A to D. And well, so remember 15.5 was saying that if fx and fy are continuous at AB, then f is differentiable at AB. Well, actually, in this case, 15.5 doesn't apply because we just found that fx and fy are just not continuous at 0, 0. I don't remember which part it was. I think it was part D. Yeah, so it was part D. We found that these two functions are not continuous. So then the theorem doesn't apply. And 15.6 doesn't apply as well. Remember, 15.6 said that if a function f is differentiable at a point, then it is continuous at a point. Well, we found that the function is not differentiable at this point, so this theorem doesn't apply. And if a theorem doesn't apply, it means that everything's consistent with the theorem. This was in part, I think it was in part B. Yes, we found that f is not differentiable. Part B. I want to summarize a few important points. First, we were given this function that was equal to 0 at a point 0, 0, and it was equal to this expression everywhere away from 0. When we were finding the partial derivative with respect to x, we found that the partial derivative was 0 at a point 0, 0, and was equal to this expression everywhere else. Now, remember, at points away from 0, we used quotient. The reason why we were allowed to use quotient rule is because this fx at points that are not 0, 0 are slopes of this function, rates of change of this function with respect to x at horizontal lines like this. So those are lines that don't touch this point 0, 0. They are lines somewhere at arbitrary, points, not here. In those situations, you're only seeing the value of this function that is given by this expression. You don't see the value at this special point, and you don't see this denominator going to 0. That's why there is no reason to do anything special at these points because this function is perfectly well behaved there. So we can just pretend that y is a constant and then differentiate this using the standard rules for differentiation, like the quotient rule. Now, when you are evaluating the derivative at 0, 0, this is much more, you need to be much more careful because the line there passes right through 0, 0. So actually, it has one of its ends at 0, 0, and the other end either to the right or to the left. Let's say here I drew to the right. So in this situation, there is two things happening. One is that this point is located where the denominator is 0. That's one issue. Second issue is that we are told that the value at this end is equal to this guy. And actually, if you were to use quotient rule and just plug in 0, 0, you will find that the answer would be undefined. So this expression is undefined at 0, 0. But that's not the only reason why we shouldn't use quotient rule for finding fx at 0, 0. The main reason, in my opinion, is that we're told the value of the function here. So you can think of it sort of this way. Let's say in 1D, when you have one independent variable, let's say I give you some sort of function and I give you that the value at this point is like this. If I ask you for the derivative at x equals 0, you can't just differentiate this guy. Let's say this guy was given by some polynomial plus something. I don't know. You can't just differentiate this guy and tell me that the derivative at this point is the derivative of this polynomial. That's not correct because the value of the function here is not what differentiation rule thinks it is. So actually, for this guy, derivative doesn't exist. So my main point I'm trying to get across is that when you have this piecewise defined function and you're asked to find a derivative at a point where this sort of stuff happens, even if this guy was well behaved, even though it's not well behaved, but even if it were well behaved, it still doesn't mean we can use differentiation rules like the quotient rule or power rule or things like this. And also no, never mind, sorry. Okay, also another thing I want to mention is why it happens that fx at 0, 0 exists, because this function is pretty nasty, right? This guy, and also this one doesn't exist at 0, 0, so it really seems kind of odd that the function, that this guy exists at 0, 0 exactly. So what I did is I plotted this guy in MATLAB. What I'm showing is the color plot of f of xy. And if you were to do the calculation, you will find that everywhere along the x-axis, the value of the function, so along the x-axis means y equals 0, the value of the function equals to what? Well, I'm not talking about 0, 0 right now, I'm just talking about this one. Plugging in y equals 0, I'm going to get minus x times 0 over x squared. Minus x times 0 over x squared, which is equal to 0, right? So everywhere on this line, I have the function equal to 0. At this point, I can't use the expression over here, but I'm told that the value at 0, 0 is equal to 0. So when you read off the entire function, you find that as long as we're just looking at the x-axis, everywhere we see the value of the function equals 0. When this happens, it means that fx at 0, 0, which is the rate of change along a line like this or along a line like this, is going to be equal to 0 because you're just seeing a constant value. Yeah, so I think that's all I wanted to discuss for this problem. Problem 99 in 15.3 gives you a function f of xy as an integral of some function h from 1 to x times y, and h here is an arbitrary continuous function, which is continuous for all real numbers. And then the question asks to find partial f partial x and partial f partial y. To solve this problem, let's consider this as a composite function. It's for this, let's call this guy u. And in this case, we will have f of xy equal to integral from 1 to u of h of s ds. And this whole thing I'm going to consider as some function of u, and I'm going to call it g. So then we have fx equal to, we have f equal to g, which depends on u, where u depends on x and y. So then we get partial g, partial u, sorry, direct g, direct u. Then partial u, partial x. And then for fy, we have dg du times partial u partial y. dg du is the derivative of this guy with respect to u, and we know that if we differentiate an integral, we will, and an integral where the independent variable is right here, then we will get the integrand evaluated at this point. And then partial u partial x is equal to y. That's what I got from here. And then this is equal to h of xy times y. For this part, it's the same thing. We have h of u times partial u partial y, so we get x. This is equal to h of xy times x. Now, you might be a bit wondering why I said that this is a function of u. Well, this is because an integral destroys any dependence on this dummy variable. So the actual dependence is on u. And I'm just showing you an example. For example, this h of s equal to s squared. If I integrate it, I'm going to get s cubed over 3, and then this integral would be from 1 to u. So then I get u cubed over 3 minus 1 over 3. And you see that this is only dependent on u. It's not dependent on s or any other variable. And then also, if you were to differentiate g with respect to u, you are going to get, well, this is the only part that's not constant. It will give you 3u squared over 3, which is u squared. And that's because, well, we integrated and then we differentiated, right? That's how we got this. Or you could use what we used here, fundamental theorem of calculus, to write it as h of u.